Module 5, we're going to be talking about methods for surveys. So when we create a survey, what we want to do is that we want to get the best sample that's going to represent our population. So remember, we want to talk about the method used for the survey, not the outcome of a single survey. So in this little picture that we have here, what we have is that the cup is the population, and each ball represents a single sample. So what we'd like to do is that we'd like our samples to get really close to the population, kind of cluster around it. So that survey method would both be precise and accurate. Now, a survey method would be precise but not accurate if all of the samples are close together but kind of miss the actual population here. So again, this would be the population, and even though all of our samples are close together, they're not actually close to our population. Now, this example is one that is not precise, but it's accurate. So if we look at all of our samples, they're all grouped around the population, but they're all fairly far away from each other. Now, the last one is just a hot mess. Our samples aren't close to population, nor are they close to each other. So in science, what we want is we want something that's going to be as close to the correct answer as we can get, and we want to be able to repeat it over and over and over to get the same result, or at least similar results. So remember, the closer the balls are together, we get better, and that is called precision. The closer the balls are to the hole, we get more accuracy. Accuracy means that we're moving in the right direction of the true population value, okay? And what this is going to do is it's going to help us reduce bias. Precision means if we do the survey over and over and over again, we're going to get about the same results, and that's going to be measured in standard error. Let's look at examples where we're going to have poor accuracy and poor precision based on our sampling method. Suppose we want to find the percentages of females taking college courses. What is a sampling method that would lead us to have poor accuracy, and what would be one that led us to have poor precision? So poor accuracy means that our values would be probably pretty close to each other, but actually far away from the true population proportion. So in most colleges these days, what we have is that we have the female population is about 60%. So we have more females going to college than men. Now what we're going to do is that we are going to take samples. Now if we take samples, and let's say that we only take samples from female-dominated fields. So let's say that we only look in nursing classes, psychology, etc. What's going to happen is that we're going to get a lot of classes that actually have a higher proportion. Now, of course, we're going to get some classes that have a lot more, and we're going to get some classes that have less. But if we repeat this sampling method over and over and over, what we're going to see is that our sampling distribution is going to give us a result that's actually higher than the population. So in this case, our p-value for the population would be less than p hat, the one for our sample. Now, poor precision, what this is going to be is this is going to be values that are going to be all over the place, but that kind of hover around the true population. So remember, the percentage of females in college is 60%. Okay? Now, let's say that instead of looking at courses that everybody needs to take, we only look at advanced courses. So let's say that we only look at, say, engineering courses, or nursing courses, or let's say that we only look at welding courses. So in welding courses, maybe we have lower percentages of females, but then in nursing courses, we have a higher percentage of females. And then maybe we look at an English course, we look at some math courses, and what happens is that if we take the averages of all these samples, they're all going to be up and down, but they're all going to kind of gather around. Now, if we compare these two distributions, you can see that even though they have the same center, our sampling distribution, which is this guy, is going to have a higher spread. So we'll come back to that later. All right, now we're going to look at a big example. So in this next example, what we are going to do is we are going to be looking at a multiple choice question. So this multiple choice question is going to have 5 choices, and the probability that we get an answer correct is going to be 20%. So our population proportion is 20%. What we're going to do is that we're going to take a random sample of 10 people, and we're going to have those 10 individuals randomly select the 5 multiple choice questions and record what proportion of them were correct. We're going to do this 20 times. So I'm going to go ahead and pull up the simulation, which is here. So I have multiple choice with 5 choices. Our sample size is going to be size 10, so we're asking 10 individuals to do this. And I'm going to generate 20 samples. So here, if I generate a single one, it has the same proportion as the actual population, which is great. If I do it again, that has a proportion of 0.1. So that means that only 10% got the question correct. So if I continue to do this, notice over here on the right-hand side, my proportion is changing for each sample that I do. So sometimes it's higher and sometimes it's lower. Okay, and finally I finish and I have 20 samples. Now, if I take all of these samples and I average them, they're going to have an average of 0.235. And they're going to have what's called a standard error of 0.153. So let's go back and answer those questions. So we repeated the survey 20 times. The summary of the sampling distribution is as follows. So this is the distribution of all of our samples, all 20 samples. So the average was 0.35, and the standard deviation was 0.153. So let's think about this. We know what distributions look like, and we know what averages and standard deviations are, but what does it mean in the context? Well, this is what it means in the context. It means the average sample will have a correctness rate of 23.5%, and then standard deviation, that means give or take 15.3%. So as far as standard deviation goes, that's not really a great estimator, is it? I mean, it's 23%, give or take 15%? That's nuts. All right, so what we're going to do is that we're going to try this again, only we're going to increase the size of our sample. So instead of having 10 people do this exercise of randomly choosing a multiple choice answer, we're going to have 50 people do it. And we're going to repeat it 20 times again. All right, so we're going to change our sample size to 50. Okay, and again, we're going to do this 20 times. So I'm just going to fast track it and hit this twice. So now that we have a larger sample of 50, but we still have 20 samples, let's see how our mean and our standard error did. So now our mean is 0.191, and our standard deviation went way down. So we're only 1% off now, whereas before we were about 3.5% off. So what this means is that the average sample will have a correctness rate of 19.1%. Give or take, now it's dropped down to 5.8%. So as we can see, our samples average, it went down a little bit and got a little bit closer to the actual true percentage, which is a 20% chance. But what really crashed down was our standard deviation. So let's keep the sample size at 50, but let's repeat this 1,000 times. So that means that we're going to have 1,000 different surveys. So let's do it. So sample size, we still want that to be 50. And now we want to do it 1,000 times. So we did it 1,000 times. And what happened is that our mean is still pretty close. It's 0.197, but our standard error remained the same. So the average sample will have a correctness rate of 19.7%, give or take 5.8%. So this is interesting. The more we repeat the survey, it doesn't really seem like it's going to affect our average that much. It also doesn't seem like it affects our standard deviation. What feels like affects our standard deviation isn't how many times we repeat the survey, it's how big our sample was. So just for fun, why don't we change our sample size to 1,000. And now let's generate one sample, 10, 100, and then 1,000. So let's see, if we do 1, we have that mean and we don't have any standard error. If we do 10, well, our mean doesn't really change. Our standard error is definitely down. If we do 100 and then we do 1,000, notice that our mean gets really, really close to our sample proportion and our standard error has definitely plummeted. So let's make some conclusions about this. So when it came to all three sample sizes, what did we learn about our estimator p hat? Well, here's what we learned. Our sample, because it was random, was really close to the population. So in math speak, p hat, which is our sample, got really close to p, which is our population proportion. So what happens to the precision as our sample gets larger? So the precision, that's how far away our samples were from each other. So as our samples got larger, our standard deviation got smaller. What that means is that our samples were closer together. So that means as the sample got larger, our precision got better. Now the last question is, what happens to the shape of our sampling distribution as our sample increases? So if we look back at this, right here we have 1,111. And if we look at this, some of our samples are going to be a little bit smaller, some of them are going to be a little bit bigger, but look at that. What is that beautiful shape you see here? Oh yeah, that is the normal curve. So what happens is that our sample distribution is going to take on a normal curve. And what's even cooler is if we look at this normal curve, the average of all those samples is going to look an awful lot like our population. That is so cool. And the standard deviation of this normal sample size, or this normal distribution, is going to be the standard error. So, continuing down, how do we do this mathematically? Well, we can't just randomly generate samples as much as we want, especially because it's a cost thing, it's a time thing. Typically what we do is that we take one sample and we try to say as much as we can about it. So we can say that we have a really great sample if the sample is, the first thing is that it's got to be random. If you pick and choose, what's going to happen is you're going to have bias, which means that your sample is going to be far away from the actual population. The second thing we want to do is we want to do samplings without replacement. So I don't want to put you back in the same pool and interview you twice. Now, if we do it without replacement, what we want to do is that we want to make sure that our sample is at least, or that our population is at least 10 times bigger than our sample. The reason for this is because we want our population to be really diverse. We want to be able to replicate this, and we want to make sure that we're getting a large enough sample that looks like our population. So as long as our sample is random, we're going to assume that we don't have any bias. So we're going to assume that the bias is 0 all the time. Now, to figure out the standard error, aka the standard deviation, the thing that gives us our precision, or how far off our sample is from the population, we're going to use this to calculate the standard error right here. So that's SE, standard error, equals the square root of a population proportion times 1 minus population proportion divided by n. Remember, the standard error is the standard deviation of our sampling distribution. The lower the standard error, the better precision of our method. So let's look at this example here. So suppose that we have 1,000 people and 25% of them are cat people. We take a random sample of 100 people. So what should we expect our sampling proportion to be? Well, Since we randomly took a sample of 100 people, we would hope that our sample would be a good reflection of our population. So what we expect is that our sample, which remember we call p hat, expected to be the same as population. So we expect it to be 25%. Now, it probably won't be exactly 25%. We're probably going to be off by a little bit. So to figure out how much we're going to be off by, we're going to find the standard error. Standard error is going to be the square root of our population proportion, which is 0.25, times 1 minus our population proportion, 0.25, divided by the size of our sample. So we took 100 people, so we're going to have a sample of size 100. All right, now rounding to 4 decimal places, we're going to get a standard error of 0. Now the most important thing in math, well, especially this class, is that we want to interpret these values. What do they mean? What it means is that we expect this sample of 100 people to be 25% cat people, give or take about 4.33%. That means if I take a random sample of 100 people, I'm probably going to have between 21 to 29 of them be cat people. By the way, by cat people, I mean people that like cats. I don't mean actual cat people. Now, in real life, the thing is that we don't usually know the true value of the population proportion. That's the whole reason we're doing stats. So instead what we do is that we estimate it by using our sample proportion. So a good rule of thumb though is if you know P, then use P. If you don't, you have to use your sample. So the very last example is suppose we're interested in the proportion of art majors to the entire college population. We find that out of a sample of 120, 37 are art majors. We want to calculate and interpret the standard error. So first off, because we didn't say that we were going to do this randomly, this is probably a biased study, but that's okay. We should carry on with the math anyway, just to get our hands dirty. So the first thing I need when I'm calculating the standard error estimate is I need to figure out what p hat is. So I know that I had 120 people in my sample total, and 37 of them with art majors. It's going to be 37 divided by 120. It's going to give me 0.3083 if I round to 4 decimal places. Now I'm going to use that to calculate the standard error estimate. So remember, the standard error estimate is going to be our p hat times 1 minus p hat divided by 120. So that's going to be 0.3083 times 1 minus 0.3083, all divided by our sample size, which remember was 120. So it's not just the affirmatives we got in our sample, it's the entire sample. So when we do that, we're going to get 0.0421 for our standard error. Now the interpretation is we expect the college population to be about 30.83% art majors, give or take 4.21%. Now, to just kind of give you a little taste of what we're getting into in the future. Okay, so notice that our sampling distribution is normal, or kind of normal. Just go with it. My picture's not great. Now remember that most of our samples were going to fall around P, and then we were like, hey, but they're going to be off by a little bit, right? And they're going to be off by that standard error. Now, because this is a normal curve and we're looking at the center and then about how far off things are from the center, we're probably going to be faced with the empirical rule again. So just think, how many of our samples are going to be within 2 standard errors of the population? How many are going to be within 1 standard error of the population?